interrupt me for each figure and provide me some feedbacks on them, because I'm not completely familiar with this field. Sometimes I know maybe I'm giving some wrong information, or there is some misunderstanding of some concepts. So totally, it's not a presentation. I just copy and paste six figures that we already have in initial draft. So I put the figures and the captions. So we will go through them, and please feel free to provide some feedback. So they would be much appreciated. So first of all, the topic is okay, Dr. Killen. I tried to write a general topic because that was not my major, and I preferred some, for instance, keyword quantum modeling, the density functional theory, and the conjugated polymer in the topic. So do you think it's work, or?
Yeah. Please, you please feel comfortable. You are the boss. You are the leader of this project. So whatever seems reasonable, do not hesitate to go forward. We will just provide minor comments on how to polish it.
Okay, that's perfect. Okay, so the first figure is the uh, schematic chemical structure of this polymer model, and the right panel figure, subfigure B, is the optimized ground state of this structure. So this current polymer model actually is a dimer that make the actually periodic model. Two monomer are connected after 100 degree rotation of the monomer to put these two middle tyrosine group in the opposite direction, one of to the bottom, one of them to the top, to make them more stable. So we thought that this could be okay for the figure 1, consists of two subfigure A and B. So in this model, the actually the yellow color represents the sulfur, the blue color represents the nitrogen, and red oxygen, cyan is carbon, and white, or it's not white, the silver color also represents the hydrogen. So any comments for this figure?
I suggest we will. Yeah. Everyone is welcome to discuss, but if it is not a critical comment, we can just type in the chat line and then go through discussion. But David is most welcome to speak anytime, because he likely will leave for teaching.
Okay. So the next step, Dr. Killen asked us to provide a schematic figure of the whole process, or whole things that we did for this study. Maybe the figure 2 could be the figure 1, or we can flip them. So this is the figure 2, Dr. Killen. As you mentioned, I just revised them and added absorption spectrum. So let's start from subfigure A. As you can see here, we just measure the ground state with both PBE and HSE06 hybrid functionals to see how the band gap value is close to the reported experimental values. So this is simple figure that represent the ground state. So after that, the excited states is tried to depict through a schema. So as we know from the band theory, so the highest there is a difference between highest occupied orbital and lowest unoccupied orbitals, HUMO and LUMO. So as we inject maybe electron or holes to the system, we expect to have some maybe additional energy level between the HUMO and LUMO, and change the HUMO and LUMO to the new orbitals, maybe to have them actually in the different energy levels. Here we did both N-typing and N-type doping and P-type doping. So figure B represents the schematic process of the N doping. So we inject 2 electrons to the system. We fill 2 unoccupied orbitals. So as you can see here, one of the orbitals is filled. So we have a new, actually HOMO here. We call it HOMO star. So the energy gap for sure is should be smaller than the previous one because the system is in the excited state, and there is a sub gap below in the location of the previous band gap. We call it E sigma here, and again the absorption spectrum versus transition energy is reported here. Vice versa for the p-type doping, we decrease 2 electrons from the system, subtract or maybe inject 2 hole to the system to have the p doping, and just wanted to show that 2 of occupied orbitals are evacuated. So the previous HOMO is substituted with a LUMO star. So again, we expect to have a lower band gap, EG, and this, for sure the sub gap E sigma is available at the previous location, and this absorption spectrum versus transition energy also is reported in the right side. For the spin polarization, so as I understand for this calculation, especially in the VASP, when I check my outcar file, I saw that the orbitals are divided into 2 components, component A and component 1 and component 2. So here each orbital is filled just with 1 electron. So the component 1, for instance, is electron to the top and the bottom electron to the bottom. So here we did again the calculation of the band gap with these 2. So one of them should have the bigger band gap and one of them a smaller band gap. So it's kind of mimicking the excited state with the spin polarization. So, and finally for figure subfigure E, we did the key point sampling to sample the beryllium zone, and so for sure there we expect to have absorption spectrum with the lower fluctuation over the transition energy. And according to my experience and also Dr. Killian comments, so we expect maybe a wider well for the absorption spectrum. So I hope that this figure can represent the whole process that we have done for this study, from the ground state to the excited state and the key point sampling. And maybe it's better, I don't know, Dr. Kuhn, it's my opinion, maybe we can flip this to figure 1 and discuss it in the method section, and put the figure 1 as the new figure 2 here, and both of them could be discussed in the method section. So
flipping figure 1 and figure 2,
yes,
seems reasonable to me.
Yeah, because I wanted to put all of them in the same figure, but it could be a whole page figure, so maybe it doesn't look good. So it's better to put this figure independently. So if you're okay, I will flip them in the next revision. Okay, could we go forward? Any comment until here? Okay, for the figure 3, Dr. Killian suggests to put all density of states for all the calculation in the same figure. As we reviewed in, excuse me, as we reviewed in the schematic figure, density of a state is presented first for the ground state. The subfigure A and subfigure B are the density of a state of the ground state. Subfigure A show the density of a state using the PBE functional. As expected, the band gap is has the value of almost 0.9, 0.89. However, the energy gap value for this kind of polymer reported around 1.3 electron volt. So PV functionals, not surprising that underestimate the band gap here. And here I just labeled the frontier orbitals around the band gap from HUMO -1 to LUMO +1 to actually mark them in the next figures in the absorption spectrum. So the next step in subfigure B, we employed the hybrid functionals, especially HSE06, to see how these hybrid functionals can provide a better approximation of the energy gap. We know that these hybrid functionals did a very good job to calculate the band gap of the semiconductors. So here the results show that the band gap of 1.2 electron volt is observed, which is very close to the reported experimental value, 1.3. However, I saw some papers also reported 1.2 electron volt as a band gap for this specific polymer model. Okay, the ground state is reported here with subfigure A and B. For subfigure C and D, we plot the density of states for the N doping and the P doping. So subfigure C is the N doping. So we inject 2 electrons to the system. We fill one more orbital with 2 electrons. So as we can see, there is as we also saw in the schematic figure, we still have the subfigure here, subgap here, but the band gap is shifted to the right, to the higher energy, and we see that the band gap is decreased, and N doping, as expected, increased the conductivity of this polymer model. So Dr. Killian, I have a question here. So for this, for instance, for subfigure C, we can see there is still a band gap in the system, because according to the density of states, we cannot observe a clear gap in between those 2 new orbitals, for instance, HUMO star and LUMO.
Will you please repeat the question? I just do not see any confusion, it seems.
Okay, sorry, maybe it's a silly question. For instance, for subfigure B, we can observe a clear band gap here, okay? The density of states have a 0 value.
Okay.
So, but here, for the subfigure C, we can see that there is any gap here. Actually, I expected have some 0 value for density of states in this new gap. Is it, we can say that still, for instance, if I check the orbital energy, the band gap here, the gap between the neo HUMO and the LUMO here is 0.3, for instance. So
you should measure distance between tops of the peaks. If one peak corresponds only to one orbital, one should measure energy offset between top of the peak, not overlap.
Oh, okay.
Stuff, because it depends on the width parameter, which is in some sense frivolous choice of a researcher.
Okay, my bad. I got it. Thank you for clarifying. Okay, so subfigure C represent actually N doping. So the P doping also is reported. The density of states is reported in the subfigure D. So we inject two holes to the system. So we evacuate two electron from the HOMO, and so that HOMO is evacuated and converted to the LUMO star. So, and again, we can see that the energy gap in the new energy gap is smaller than the original gap, as you can see here. The next two figures, sub-figures E and F. Sub-figure E stands for spin polarization. So, as we discussed in previous figure, the orbital energy are split into two components, spin up and spin down, and the band gap show a kind of excitation, and again have a smaller value here. And the latest one for sub-figure F, it's a little more blind for me comparing to the other figures. We use the Fermi comment here to mimic kind of excitation states. So actually, two electrons are promoted from HOMO to LUMO. So HOMO is empty, and we shifted that HOMO to a new energy level. And this right shifting of the energy gap ended in a smaller gap value, kind of excited state. I also have this question, Dr. Kilin. When we did the p doping and n doping, why we need to use Fermi to mimic the excitation state? What is the main reason of subfigure F in our calculations?
First, this green thing should be shifted to the left between peaks at -3.5 and -3.
Okay. Sorry, my
Because
mistake.
it was former HOMO and former LUMO.
Okay.
I know that Mead has connected to our meeting. Mead, would you like to share your personal opinion? What is the value or what is interesting in promoting electron from HOMO to LUMO? And you may want to enable the microphone or connect to your phone or type in the chat line. Okay, maybe there is some issues with microphone on Meet side, but you're very welcome to bring your comment. Amir, if you were listening the presentation of Mead last week,
Yeah.
so the whole story of his research is breaking of a molecule through photoexcitation. So his work was on photodegradation. So if one promotes an electron from HOMO to LUMO, the molecule becomes unstable. And if you enable molecular dynamics, it may break onto pieces.
Okay.
If it is originally not very stable. If it is quite stable, it just changes geometry a little bit and then emits energy and shares electron and hole at slightly different energy compared to unexcited molecule.
Okay. Okay. Good.
Mir, is it you? I hear someone is putting microphone on. No. Okay. I hope I didn't answer instead of Mir. Amir, does it make sense?
Yes. So when we want to discuss this subfigure, we can say that it can provide more insight into the excitation state of this kind of polymers.
Right. Soft materials experience change in geometry in response to photoexcitation. And sometimes it is a leading factor in their progress. Since you are the main person in this project, you're probably screening experimental literature, and you do know which effect is more important for this material. But if you do systematic exploration of all possible mechanisms, this one, response of geometry to photoexcitation, is subject to be one of the leading effects.
Okay. Okay. Yeah, very good point. I will try to connect that to those experimental data. Just one more question. Over our schematic figure, I didn't put any schema for the Fermi electron promotion. Do we need that?
Would be great. Would be great. Yes.
So if I let me come back. Just if I want to add that, it should be similar to the.
No, no, it will be not similar to anything in what is shown. Let me quickly. If you temporarily stop sharing and I will start sharing, I will try to add. Do you see the slide that you were asking about?
Yes.
Okay. I would do something like this, but you're free to modify and tell whatever thing seems reasonable to you. So here is the geometry in the equilibrium, and upon you excite to the first excited state, the geometry is experiencing reorganization to different value of internuclear distance, and then the energy offset for the excitation becomes smaller than it was originally for unexcited system.
Okay, makes sense. So we excite the system and let it to try to optimize the geometry with different potential energy surface, with different level of energy surface. Okay.
So I'm stopping to share, and feel free to.
Okay, thank you for the comment. You have my screen. Okay, the next results are the key point sampling results, actually the frontier orbitals for the both PBE and actually HSE06. So here a direct band gap is observed for this polymer model. And so just to make a clarification, to do this key point sampling, we utilized 16 different key points, and I was not familiar with the process, so I did it just manually, 16 jobs for just write a bash script, run 16 different actually jobs for each key points, and then the band energy results are plotted versus the key point value, and later on the absorption spectrum is reported as a average value for this key point. And here over the key point sampling, if we consider this value as the band gap, we observe a smaller band gap from the PV functionals, and but for the HSE06, the band gap value is the same that we had in the previous slide. So if we reference the HSE06 as a most precise band gap in the current study, we didn't see a big change in that value here. Yeah, the observation maybe is noticeable here is that the band gap was direct, and I don't know which kind of useful information we can get here. Yeah, we did some mass calculation, effective mass of electron and holes also. I didn't report here, but we can discuss in the text later on. Any comment on this figure, Dr. Killian or other students?
Keep going.
Okay, the figure 5 shows the distribution of the charge density over the backbone for four frontier orbitals. From the left, it is HOMO minus 1. This is the B is HOMO, and the subfigure C is the LUMO. And for the HOMO and LUMO, if you can see that we have a maximum amount of, for instance, for HOMO, maximum amount of charge is appeared in the previously I named it Pirol, but it's David told me that's wrong. I forget the name again. Around the nitrogen, but all the tyrosine groups along the backbone have a good amount of the charge density. So this delocalized charge density to the backbone makes this orbital conductive, actually. So also for the LUMO, for orbital 313, again we observe the maximum amount of charge on these oxygen atoms. However, again, the good amount of charge is delocalized through the backbone. So this also makes this orbitals be conductive. Just need to clarify that for the excited states and the charge density, we just use the PBE functionals, and the HSE functionals just are done for the band gap calculations and some key point sampling. Okay, and the latest figure is the absorption spectrum. We did absorption spectrum with both PBE functional and HSE06 for the ground state. So sub-figure A and B are the results without sampling. However, for sub-figure C and D, we did the results after the sampling with both PBE and HSE06 functionals. So sub-figure D represent the HSE06 absorption spectrum after key point sampling. This red plot show the experimental results for this kind of polymer, which is plotted as a film. So from these results, we can see that, for instance, in our results, absorption spectra appeared around 715 nanometer wavelength, but the experimental results are around 800. We can see that our hybrid functional model predict almost a precise approximation from the about the peak of this model. However, if we take a look through the PBE functional, we can see that the right peak is much far from the experimental values. And also subfigure E and F are reported for the absorption spectrum of the excited states from the n-doping and also the p-doping. So also the transition energy, if subfigure A and B, transition energy between different orbitals are plotted from. So as expected, for instance, for the top figure absorption spectrum, for instance, the transition energy from B to C, from HOMO to LUMO, show the highest wavelength here, equivalent to the lowest transition energy. And yeah, this is that all I can say about this figure. So this could be the last figure of our study. So I appreciate any comment if Dr. Killeen or other researchers.
I mean, everyone is typing questions. Maybe when you finish presentation, we'll go line by line with all comments. And just quick question: why the red line is offset? Is there any physical or chemical
Uh,
reason, or it just looks better this way?
uh, uh, you mean about the fluctuation of our
Yes,
results, Dr. Killeen?
the red experimental result looks like there is a absorption, non-zero absorption equals to 0.4 arbitrary unit at any wavelength.
It's a very good question. Also, I think about that, but
If you do not have experimental evidences for model absorbing light at any wavelengths, just move it down by 0.4.
uh, okay, okay, I will read more about that and double check that. Also, there is usually a big difference between the peak in the y direction. Usually, it's because of the different normalizing
Yes,
process. So we do not take care about that or
what you
normalize them.
shown here is not bad. It is quite reasonable.
I think I normalize their data with
Mhm.
maximum value to just get it closer in the vertical values for the absorption.
Mhm.
Also, I will try to get maybe add more experimental value because I saw that, for instance, in another paper that was not the compatible, was not exactly the same with our polymer model. Maybe side group was different, but their wavelength was reported around 800, a little below 800, so maybe a little closer to our data. I will do my best to add more experimental data to this plot. Uh, After this, Dr. Killian asked me to put the method section. Dr. Fatima helped me to provide this part, but I didn't work on this part a lot. There are some I just copy and paste them from previous drafts. Also, so first of all, from the DFT calculation, we utilize the WASP software, as you know, and the modeling is started on the one electron Korn-Shum equation. So we can write this equation in the draft. So equation above the first term represent the kinetic energy. So everybody knows that. Uh, it's apparent that Hamiltonian orbital energy of all of them are dependent on the momentum. So the solution of the equation is reported as below from the momentum dependent orbitals. Again, I need to go in detail, Dr. Killian, and provide more information. In the draft, I will improve them. So the total density of electron is a combination of the orbitals and the orbital occupation function of ik, which is reported as here, and the total density provides the potential as this equation. Here, the potential is defined as a functional derivative of total energy with respect to the variation of the total density, so which includes interaction of electrons with ions and three electron interactions such as Coulombic correlation and exchange. So um, the momentum dispersion is plotted as zero. The partial density of states for given momentum is represented by this well-known equation. So the energy of given orbital epsilon ik and the index I runs over all calculated bands. So the Dirac delta function is modeled using I don't know exactly the name, Laurentian. I'm not wrong. And finally, density of states could be plotted over the K as the following function. Also, absorption spectrum are calculated based on the independent orbital approximation, which are reported here, the formula and the process to measure the absorption spectrum. Again, I need to work more on the method section. For instance, for the spin polarization, Fatima shared one of the add-on papers. I take a look. I will use that draft maybe to read more about the spin polarization, how to add it to the method section. But I not sure about the reference for the Fermi calculation. So if somebody can provide me some tips how to write the method section for Fermi calculation, could be very useful. And also the method section related to the hybrid functional, I need to add them in detail in the method section. I gather the important papers from this HSE, and I will summarize them in the hybrid functional. Just a brief illustration of this hybrid functionals are reported here. So I will return paper to you as soon as I finish the method section as it should be. So here is the last slide.
Okay, please join me thanking Amir for interesting presentation. And let's go to the first slide and maybe read the comments and discuss. Okay. No, the very first slide.
The first slide. Let me just minimize this.
So very close to the end of the list of the questions, and you probably can see the list of the questions yourself, right?
Actually, I need to stop sharing if I want to see the...
Oh, no, do not stop sharing. I will read them out.
Okay, thank you.
Very close to the end of the list of the comments, there was a question of Yulun, and then at the beginning there is a similar question for myself. So I'll read a question from Yulun. It's about a paragraph. So the overall impression is that you are trying to characterize the ground state properties of the conjugated polymer. Is this the goal? Why this is important? Do you get results in good agreement with experimental results? HC06 is better and is available for your system. Why do you need PBE?
Thank you, Dr. Han. That's a very good question, a general question. Need to review all the papers. So, to answer this question, first of all, yes, the first goal of this study is to explore the ground state of this polymer model and explore the band gap and the absorption spectrum. So this is a very important polymer model which is broadly utilized recently, usually the conjugated polymer. So this specific polymer show very good optical properties. So that was our goal, to investigate this polymer first. Yes, we start with PBE functional and then use the HSE06 functional to predict the band gap. And as we saw, HSE06 provide very good approximation for this polymer model. Why we use if HSE06 provide very good information or prediction, why we use PBE functional? So maybe exploring the excited state with HSE06 is very time consuming and computationally is very expensive. So we just take a look through the ground state and the band gap calculation and absorption spectrum with the HSE06. But for the rest of the calculation, especially the ground state, we just rely on PBE functional to do some not quantitative study, just some qualitative research on the excited state of this polymer, for instance, via spin polarization, via doping, either N doping or P doping, and also promotion electron with the Fermi calculations. So PBE functionals are more available and computationally less expensive for this purpose. But HSE just we try to maybe examine the band gap energy that people usually find in the experiments. So these computational values can first show that DFT calculations are very powerful to approximate the experimental value. Also, this value can be a start point for the synthesized people maybe who want to work experimentally in this kind of the polymers.
Yun, does it answer your question? Or not enough?
Sort of, but I guess in this work you are not doing any excited state dynamics, right?
No, we didn't. We did actually started some molecular dynamic jobs, but not added to the results. Maybe as a follow-up study, or I don't know, maybe we can find sometimes to add those results to the current paper. It depends on the near future.
Okay, so I guess my question is, the ground state calculations is very cheap and it's available for everyone. What makes your study special?
If we maybe the excited state of this polymer is the novelty of this job. If we just take a look at not the molecular dynamics.
Yeah. Let me translate. Yun is asking question in a very gentle and polite form, but let me translate it in a more rude form, how it may sound from the reviewer.
Okay.
Reviewer may say, if authors will not redo all calculations with HSE, I recommend to reject this paper.
Okay. I hope not to receive such a
So, to my personal opinion, the main task for you now is to arrange pieces of your paper in a logical way to compose a story.
Okay.
But be ready that upon you submit the paper, you may get such a reviewer's report that will demand to redo every single calculation with HSE.
Okay, makes sense. Yeah.
And you may start these calculations right now. So you do not let your team to wait until you are done. Keep working on telling the story, but just keep it in mind. And
okay.
Let me also help you in answering Yvonne's question, like what is the value of the work?
Mm-hmm.
And it is not my original answer. It's kind of a standard answer that can be standard reply to such question in most of the works we are doing. The calculations that you have done allow to inspect the trends in this material, the general trends, general properties, and absolute values, quantitative metrics of the effects that you are computing can be better or worse with details of calculation, but basic ideas that internuclear distance change upon excitation, that internuclear distance change upon injection of charge, that dispersion over K points provide additional broadening they're not very new, but they are qualitatively correct, and they are important effects that your calculations are catching. So you're telling the trends, the main effects that play the role in properties of this material. And of course, with better functional, the quantitative metrics will be better and more valuable for comparison to experiment. But based on applications of functionals to different systems, it doesn't look that it will be drastic qualitative change of the properties by switching functional. So it doesn't mean that you shouldn't slowly plan on resubmitting all jobs with HSE. But this is not task number one. Task number one is to compose the story. Okay, let's go. So first question in the sequence for myself: what is the goal of the modeling? What is the missing knowledge in the community?
Missing knowledge. From the few experimental papers that I read for this polymer model, people also are interested in the influence of the changing temperature on, for instance, absorption spectrum of this kind of polymers.
So you shouldn't tell it, because in this paper you do not show dependence on temperature. What else is missing? Like, tell only those missing points in the community which your paper is addressing.
Which we are addressing right now. The band gap value, maybe?
No. Again, the exact values is very unstable ground. It's like walking on a swamp. And HSE is better, but next year maybe there will be better functional. Look on the trends, which fundamental knowledge, not exact values, which mechanisms, which trends are not clear in the community.
Maybe the performance of this polymer model under the excitation states, for instance, under the doping, under the photodegradation, photoexcitation, or something like that, could be the main advantage of this polymer model that can provide some insight into the behavior of this polymer under excitation that can help some maybe synthesized people or experimental people to have some prediction of the performance of this material before going, for instance, for a multi-step synthesized process.
Mm-hmm. It is an excellent answer, and it will be really great for the introduction. Okay. What is P? What is D? What is P? What is P in your PDPP? It should be in the figure caption.
Oh my God!
Tell it right now.
I should bring a pair. This is a very big name, Dr. Kirin, and maybe 100 alphabet. The name of this polymer is very complex, and the people just extract some of the extraction for that. If you let me, I can read that for you.
At least Mead is curious and enthusiastic to learn the name.
Okay, please give me 1 minute.
You can just copy paste it from if you have some PDF sources open, you can just copy paste them into the chat line.
Okay.
Please verbalize, read it out.
Sure. So I need to stop sharing when I want to put
Okay, you can stop sharing and then start sharing again.
Okay. Okay, Mead, this is the name. If you can read that, please help us.
So let's chop it, because otherwise it will be 100. So first is poly. Second is D. D-keto. The third is pyrrolo. PO. And the pyrrole. P, so poly, decatur, pyrrole.
Right.
Okay. Poly, decatur, pyrrole. Okay. I'm a little surprised that the word thiophan is not spelled in the title of this polymer. It's a little strange, but I'm not an organic chemist by training. But if I would be naming this stuff, I would put that that it is polythiophene, and then add this thing after. Okay, we start
right.
sharing again.
Okay, let's start sharing. So,
okay. Next question from Yvonne about the structure tells that structure A seems more complicated than B.
you mean about the figure 1?
Yes.
So figure B is plotted by VMD. Figure A, I just plot with some ChemDraw softwares, for instance. Here, I just prefer to draw it by PowerPoint.
So maybe to avoid such questions, and so look at our meetings as we are trying to find weak places that you can fix and get easier through the reviewer's criticism. So there is nothing in principle in this question, but it just helps you to get through reviewing easier. You may add into the figure caption that trivial alkyl chains are abbreviated as CNH2N+2. Something like alkyl chains are abbreviated as CNH2N+2.
Okay, I will.
It will just avoid unnecessary questions.
For sure. Thank you for the comment. I will revise that. So Dr. Kilin, may I ask a question?
Please.
I told that if you remember in the beginning of the chemistry project last semester, you mentioned that it's better to rotate these two monomer to connect them after 180 degree rotation. So then in the middle, it put this thiophene group in opposite direction. So the reason is that this makes the system more stable, or?
Yes.
I know some.
So okay. I do not have positive knowledge. It's only intuition, but it reduces the strain. So if you will have all sulfur parts of the thiophene to the same side, it will make the molecule to bend and create additional strain. If they are flipped in the opposite at each bond, it much less strain and it looks more linear.
So it's mostly for computational purposes, because
no. If you look through structures practiced by polymer chemists, especially, I think there is a major expert at NDSU for experiment is Professor Seth Rasmussen, and he is exploring polymers like thiophene for photovoltaic cells. Well, you don't need specifically contact him, but if you look through the literature on polythiophene, you'll notice that it is a typical arrangement when they are flipped.
Okay, thank you. Because for this polymer, especially in glass transition and mechanical properties, we have very powerful group from the University of Southern Mississippi.
Mhm.
So I show some results of this conductivity through my mechanical results, and he was interested to see if what happened if we put, for instance, that two thiophene in the same direction.
Mhm.
Uh,
Yep.
as an experimental, that was an interesting point for them, because he said that through the polymerization and packing the system, even thin film or bulk model is not available for synthesized people to adjust or control completely the polymerization. So maybe some thiophene are in the opposite direction. It's kind of random
Mhm.
polymerization method. So from the experimental guide, maybe people ask them, is it compatible with the real synthesize of the polymer model, or no, it's just an ideal case from the computational.
It is very legitimate question, and it can be another chapter in the research.
Okay,
Intuitively, no, too early to say anything intuitive. Let's focus on this first.
okay, I got it.
Okay. So further, the major thing, it's a comment from David Graupner. The major thing is that pyrimidine rings are flipped.
Or flipped, what does that mean? Uh,
I would ask, what is pyrimidine rings?
oh, the rings, including the nitrogen, if I'm not wrong.
Okay.
So when I check the system, Dr. Killian, in the other sides, for instance, from the Z direction, the
Mhm.
whole backbone is in the same plane.
Mhm.
So, but no, I think it is as it should be. Mm, mm,
Well, what you can plan to do is to mention in the description of the system that the things that you were already telling, that during synthesis, fabrication of various isomers is possible, various local minima of this polymer. But we're exploring only one example because electronic structure takes time.
mhm.
Mm.
Okay, okay, sure.
Then figure, next question is from Aaron, and it is about, I believe it is about next slide.
Okay.
So he's asking, figure 2D, is change of spin configuration important for these materials?
So according to the results are not reported here but discussed in the text, yes, the smaller band gap is observed after spin polymerization. So it means that this kind of excitation will increase the conductivity of this polymer. I don't know if this is a right answer to the Aaron question, or more details should be provided here.
Aaron, is it sufficient? Does it answer your question?
I don't know, not really.
I
So I
don't know,
guess
I saw your paper. I know you have very good knowledge in this field, and I would appreciate that also if you give me some comments and tips on this calculation.
well, I guess you didn't talk about it much in your presentation, so it's kind of hard to ask about questions. But usually, if you're talking about changes of spin, that's like I don't know. So I think I got from your presentation, you basically just consider the lowest excited state, the lowest energy total excited state, and so those are usually triplets. So that requires a change in spin.
Okay.
Let me contribute to the discussion. So I'm going to give a comment about molecules which are not conjugated and periodic. So if a molecule absorbs well but emits but does not emit, it could be a signature that upon excitation from singlet to singlet, it flips the spin and stops emitting because emission from triplet is less efficient. So if you have experimental evidences that this polymer is absorbing light but not emitting, it may but may not. It opens the door for the probability that spin flip and triplet configurations are important for this system. At least it makes it a suspect.
Okay, I would be more curious about this point, Dr. Killen. That was very important. Thank you. And I read some experimental papers.
Next question from Aaron. Figure 2E, relation between K point bands and absorption spectra seems odd.
Seems what? Sorry.
Seems odd. So, Aaron, would you like to specify your criticism?
So I guess in the left half, you're showing that the band gap, not necessarily the gap increases, but you have increasing transition energies.
Okay.
Different momenta. But your figure on the right of that, it doesn't really, at least to me, it doesn't really like show how that would show up in the absorption spectra.
Amir, would you please stop sharing for a second? I'll share and we'll try to do teamwork in convincing Aaron.
Okay, thank you.
So, do you see my screen?
Yes.
Okay, so I'm just checking if the following visual presentation will convince Aaron. Arrow number 1. Arrow number 2. Arrow number 3. Arrow number 4. And so forth. So instead of one transition, we have like a collection of individual transitions that provides increase of the width. So it starts absorbing not at a single wavelength, but in a range.
Yeah, that makes sense. But then why, I guess in the schematic, like E gap should be at your
lower E gap should be at the lower part of this near the smaller, shortest line. Not in the middle, but at the lowest edge of this profile. Okay, Amir, I think as a team, we have some moderate success in convincing Aaron. But now please tell if you agree with this argumentation.
Actually, I get confused. Maybe it's because of my lack of knowledge in this field. So I always expect if I draw for instance, the orbitals for different key point value, sometimes we have a direct band gap, sometimes indirect band gaps. So here, an indirect band gap is observed. And
no, it is direct. It is direct.
Sorry, a direct band gap is observed. So this band gap should be equivalent to the peak of the transition energy, shouldn't be?
No, no, it is the lowest energy at which system is absorbing. Aaron, would you please try to share your vision of the system as you see it? Just maybe 1 or 2 sentences as you see the situation.
I think your figure, or the figure that you drew out, explains it. So it's like your E gap would be like your absorption where it begins, but then any feature, but then all the other features will be blue shifted from it, or it'll be higher in energy. So they have to be higher energy on your transition energy axis.
Okay.
I'm happy with it. Amir, are you happy? Or not quite?
Need to maybe study more about that, think more about that, but
Okay.
it's not still clear for me. Thank you anyway from Aaron and you.
Okay. Then please start sharing again, and let's go over the rest of the comments.
Sure. So Dr. Kinney, that plot E was incorrect, right? This shouldn't be EG.
I didn't pay attention to it, but for Aaron it was confusing. So yes, I think if you make this line shorter so that it goes not to the gray area but to the lowest edge of this green profile, then it will be much less. Yes, yes.
And what about the peak? Which part is related to that peak? How we call it?
One of the gray lines. One of the gray lines here.
So we do that. We don't know which one is related to peak.
No. It's the whole profile is a collection of individual transitions at different values of.
Okay. Oh, okay.
Okay, let's go further. Slide 3. So the question from myself: other experimental evidences which tell which mechanism of shown in this figure is more or less important in this class of materials?
Mm.
I do not know if there is an answer, but when you partially addressed it, so that at least the response of the conjugated polymers to photoexcitation and injection of charges is not quite clear. Therefore, they need to be explored.
Right. I will try to emphasize in these points in the story.
So from the figure and caption, it's the next question for myself. It was not clear, were you optimizing geometry for each of the panels? Is it single point, the same as for ground state, or after you make change to electronic configuration, you re-optimize the geometry?
So yes, we change the, for instance, inject the electron and optimize the system again.
Okay, so it definitely needs to be in the text and maybe emphasize it in the figure caption to avoid unnecessary questions.
Okay, sure.
And this change of geometry upon injection of charge or upon excitation could be most appreciated part of your work. We do not know until the work is being read by reviewers and readers, but maybe it would be most interesting part.
We discussed it before, Dr. Killian. I plot the geometry of the system for three states: the ground state, the N doping, and P doping. They are very close to each other. So
do not worry if they're close, and maybe talk to Aaron or look through his paper on tolerance. Aaron did design a way to emphasize their change. So maybe he's showing arrows near atoms to specify in which direction ion is moving, even if it is not seen by human eye. But do not focus on it right now. It is a, even if it could be important, right now the task number one is to compose an interesting story where all things are all parts are connected.
Okay, thank you. Thank you. Especially, I appreciate all these comments. They will address the points that I do not have enough knowledge in that area. So help me to come back and take a look through some references. I appreciate these questions.
So David Grobner is asking, what is, maybe it is about next slide. Can you please flip to the next slide?
Sure.
Okay, so David Grobner is asking, what is the CP model? And I did answer to him that C means conjugated, P means polymer. Was I right answering him?
For sure, yeah. I will revise that. Yeah, it's better do not use abbreviation maybe in the figure captions, because people maybe sometimes do not read the entire text but just directly go to the figures in the paper. So I usually do not use abbreviation.
Mm-hmm.
I will revise that. But yes, CP stands for conjugated polymers.
Is there a table? Next question: is there a table for total energy for each of the configurations from panels in Figure 3A to F?
Type of what, Dr. Klein?
Like in Figure 3, you show density of states for different electronic configurations, right?
Right.
For each electronic configuration, you can extract total energy out of VASP. Do you plan to include a table that will show total energy of each configuration?
Should we do that?
Yes, and it shouldn't be difficult. It's like maybe 10 minutes activity.
And for sure, yeah. I will address all of them in a table. I remember you mentioned this before. Sorry, I forgot to do that, but I will provide that table.
Yeah, thank you. Next question is from Aaron about Figure 3. Is there a connection between panel E and panel F?
Good question, Aaron. So, as I discussed them briefly in the discussion part of the paper, these two figure E and figure F, are mimicking the excitation state. So in the figure E, we regulate the spin direction of the electrons. In figure F, via Fermi command, we promote two electrons from occupied orbital to unoccupied orbital.
Aaron, sorry. If Amir, if you are continuing, please continue.
Yeah, so that is just maybe mimic the excited state.
Let's check with Aaron. Did Amir answer your question?
So I guess is it just two different calculations, checking for which configuration has the lowest excited state energy? Because I guess E and F, they're both excited states, but it seems they're trying to compare to each other, but it's just not obvious how they're compared.
Let me contribute to the discussion.
For sure.
Amir, would you please flip 2 slides back? Okay, not yeah, here. So let's look on the panel D here.
Okay.
So there are two. Well, in actual panel D, there are several sub panels. So the one in the middle shows that the red electron, spin up electron, is promoting from HOMO to LUMO. This is some sort of Fermi excitation. In the left part, the red electron is moving up and to the right. So from red it becomes blue. Right? Mm-hmm. As it is shown here. Maybe, and I would probably do blue electron becomes red. Just change the, make arrow from blue HOMO to red LUMO. And then it will absolutely correspond to the triplet dose that you are showing in the next figure. So both of these things, excitations without spin flip and excitation with spin flip, are both excited states. So they're just two aspects of going from ground to something more excited. On the other thing, in substantial amount of experimental systems, first, one is exciting system in a singlet without spin flip. So red electron goes up from HOMO to LUMO. And then through system crossing, it converts to the triplet. So it goes to the spin flip configuration. In this work, in this calculation, you are not computing the mechanics of such transition. But on experiment, it is a process that often happens. So now let's go forward to the next slide. By creating excitation shown in the panel F, after a very long waiting time, the system may automatically jump into excitation shown in the panel E. So it is too complicated and too much for this first paper, but it is a possible experimental scenario. Let's check with Aaron if our team work answer was convincing.
So E is triplet and F is singlet?
Mm-hmm.
That makes sense. But I guess, I don't know, to me it just seems odd that you can also do singlet and triplet. I guess it just seems kind of inconsistent because it's some are spin restricted and then some are spin polarized. So it's
I agree.
So you can do singlet and so just looking at it, it seems odd, but it's something that's
to be more consistent. One may, Amir, please do not do the following. What I'm telling to Aaron in the next 10 seconds. I'm just using it as a verbal argument. So one could redo panel F in the same format as panel E, showing symmetric up and down things. With keeping spin down unchanged and having spin up promoted from HOMO to LUMO. So it would be more consistent, but probably too much for right now. If reviewer will come after us, we may do it. Okay, Amir, I think Aaron.
Okay. I saw that there is a typo. Also, typo is a mistake.
No,
it should be
no.
shaped.
What you are showing is HOMO beta. So electron was taken from here and promoted to LUMO alpha.
Okay.
You can show it by your mouse once again, where you were showing, yeah, this is HOMO beta, and now show red spike at -3.
Yeah.
And this is LUMO alpha.
Okay.
Whew. Okay, I think it is a productive discussion.
Is there any more question?
Oh yes, yes. We went about through the half of them. You see, your work doesn't leave audience cold-blooded. Everyone is so interested.
Okay, I'm happy to that.
So David just makes a comment about the namings, then Mead telling that he was helping an undergrad, then question from myself that we already discussed, figure 6D. So 6D. Why, yes, why red line is offset by 0.4 in y direction?
I need to check that.
Okay, yeah. Next question from Mead.
Okay, I think I mistyped this one, but I can explain myself a little bit further.
Oh, question about the previous slide, one slide back, about slide 6, figure 5. Yes.
Yeah, so you might have to zoom in, but like if you look at part figure B,
okay,
and I'm going to call it a Ferrand group, but it probably isn't because what, it has a sulfur. Is that what you said? It has a
sulfur,
yeah, but thiopine is chemically similar to furan. Yes.
Okay. Well, the group that's similar to furan, kind of right in the center. Do you know what that electron density matches kind of what we're seeing with my work? And then if you look on the very next figure of C, it goes the electron density of that furan in the center switches to like the connecting carbons rather than the carbons inside of the furan group.
Right. But here maybe most important for this part of the study that the charge is completely delocalized through the backbone. So yeah, for the panel C, for the actually LUMO, we have some charge around the sulfur and as well as the carbons. So, but maybe in figure B we do not have such that charge on the sulfur. But if you look at the bottom panels, the charge is completely distributed and delocalized through the backbone. So this makes that conductive, and that was the point that was attractive to me. So, but this point also was interesting that you pay attention.
Well, yeah, I'm just noticing like just something that's similar, like with that type of group. They have similar shape with my polymer and yours, and they're exhibiting like the same, let's say, electron density. So,
okay.
Yeah, I'm going to add a comment to this discussion because it is really interesting and it may have some fundamental knowledge. Many thanks, Mead, for focusing our attention on it. So, Amir, would you please stop sharing and let me do something, and then you'll start sharing back.
Sure.
Okay. So, for the HOMO, do you see my screen?
Yes.
Okay, so for the HOMO, we do see charge density, which is in blue, repeating this pattern of conjugated bond. So if you look on the slide 7, figure 6, you'll see that the electronic clouds are showing the areas where the additional where conjugated bond is drawn, right?
Right.
Now, if we go to LUMO, I will go to the next slide. It also shows conjugation path, but now it shows alternating. So where it was single bond, now it is double. Where it was double bond, now it is single. So it so I will just click forwards and backwards here and there. So this alternation of single and double may have some fundamental property related to the motion of charge. I don't have better words, but it looks very much relevant to the chemical structure of this polymer.
Very interesting details. Thank you. Thank you.
So your calculation just shows this alternation of the bond. Okay, you can continue sharing.
Sure.
Mid, do you have your question answered?
Yeah, that kind of alternation between HOMO and LUMO, is that pretty common with, this type of group in any polymer? Is this not really studied that much? Because it seems like if we find this in two different varying polymers, it's kind of unique. Maybe something to be looked into. I just don't know how common knowledge that is.
For conjugated polymers, and as well as graphene, carbon nanotubes, it should be common. So this conjugated bond, it means electron can move in space by alternating between single and double bonds. And I think if you read literature and speak to professional polymer scientists who work with conjugated polymers, you hear this information in maybe in a slightly different language, but it will be echoed.
Yeah, okay. Yeah, I can look more into it. Yeah, it makes sense. Thank you.
Then next question from Yvonne. I think we already discussed it. The overall impression is that you are trying to characterize the groups, the ground state properties of the conjugated polymer. Is this the goal? Why this is important? Do you get result in good agreement with experimental results? HSE is better and is available for a system. Why do you need PVE?
I think we discussed that, yes.
Yeah, we discussed, and from this point of view, the main result is your figure 7D, or figure 6D. Next slide. Yeah, panel D, where experimental and computed spectra are in some partial agreement.
Right, yeah, from the visualization point, yeah, we have just this figure, but also we have some references to discuss in the text how, for instance, doping of this kind of polymer is investigated in the laboratories and how it is related to our research.
Okay. Let's go to next slide.
That was the last one.
No, we are going to equations. So you do have k point as a vector k, and by the way, once it is vector, another time in the potential it is without vector. So I do have a little question: should the k vector enter into the kinetic energy? Do not answer right now. Just make a note and explore this question.
Sure, I will.
Right now, your kinetic energy is only gradient over position, but maybe it should be also like gradient squared plus k squared. Just double check.
I will for sure. I didn't go through the details for metal
Sure.
section.
Do not worry. You have time for this. And we'll debate whether to put equations up front, all equations to the paper, or maybe move them to supporting information. But there is no way to avoid them. They need to be either here or there.
Okay, at the first draft, let's keep them whole of them in the draft, and then we can make decision. It's better
Exactly.
to.
This is very wise approach. Yeah, thank you.
Okay.
So please, I hope in the draft you will give numbers to each equation, right?
For sure, yeah.
Okay. Slide number 10. So 2 slides forward. One more. Yes. So in the bottom equation, you are adding together partial contributions from each K point. So it is density of state that accumulates all K points. I do not remember you showing such figure. You were showing absorption that accumulates contributions from each K point, but you are not showing density of states that implement this equation. So you may decide either to remove the equation or to add one more panel in the figure.
I got it.
Okay.
I tried previously to plot density of a state over all key points, but they show kind of
Messy? Too much overlap?
Too much overlap and just a line,
okay.
any gap or something like that.
Let's discuss it later. I just I'm not criticizing your work. I'm just picking logical inconsistencies.
Okay, sure.
So slide number 12. So 2 slides forward. Yes. So for spin polarization, you were mentioning that you need a source for.
I saw iron paper. It looks good, and I can use that as a first step to read those references and also reference the relevant papers.
And check. Maybe you can check with personally with Aaron in the email. He puts a lot of advanced equations, but maybe you can consult with him if one wants to summarize the essence, how to get 1 or 2 equations that summarizes the nuclear reorganization upon injection without going into too many details. Because otherwise you will have the whole, if you include all details about all your calculations, this will be not a paper, but a doctoral thesis. You need to squeeze something.
Sure, I will.
And about further calculations.
How do you name it in the computational chemistry? Like in this process, Fermi calculation is a common name for such that calculation?
No, it's only for VASP, but it is excited state optimization. If you want to look in the literature.
And I would appreciate that if you provide some tips how to find the reference.
But check, you are probably already watching through the papers by Yvonne. And I think he's doing really good work in being brief in equations.
Okay.
When it deals with this optimization in the excited state. And I believe Mead will need to have these equations as well in his next iteration.
Okay. I will check the Dr. Hahn papers.
Okay. So I think we went over the whole list of questions. Let's thank Amir for answering all of them and all contributors to the session for discussion.
My pleasure. Thank you.